Welcome to Lecture 2.2, Tautology and Contradiction. One way to motivate this topic is by looking at the application of digital electronic circuits, which are made from large collections of logic gates. These are physical devices that implement Boolean functions. We'll start with the AND logic gate as an example. A picture is worth 1,000 words. So consider this diagram down here. Here we have a battery and a closed circuit, and a light bulb. So the bulb will be on if there is a current flowing from one end of the battery to the other and through the bulb. And that will happen if these two switches, which are located on the circuit sequentially, A and B, are both in the on position, which is what they're shown right here. So here, let's say A equals 1 and B equals 1. Of course, the other possibility is that one or both of these could be in the off position like this. Here we'll say A equals 0 in this case, and maybe B is still in the on position, B equals 1. But if either one of these is in the off position, then the circuit will be broken and the light will be off. So the light, Y, is going to be on if and only if A and B are both on. This is, of course, represented by a truth table. We saw this in the previous lecture. And we can write this as a Boolean expression several ways. We can say A and B is equal to Y using the conjunction symbol. We can just write out A and B, something like this. Sometimes it's written the AND function of A and B. There's different ways to do this. But here's one I don't think I showed you before. It's A times B equals Y. Sometimes AND is represented by multiplication because in this case, if you multiply the value of A times the value of B, you get precisely the value of Y. So 0 times 0 is 0, 0 times 1, 1 times 0 are both equal to 0, and 1 times 1 equals 1. Finally, this diagram schematically is represented with this, looks like a elongated capital D. So on the left you have two inputs, A and B, going in, and the output, Y, goes out. So you can think of it as these are inputs, and the output is going to be on, or 1, if and only if both A and B are 1. Okay, that's the AND logic gate. We come to the OR gate next. Once again, we have a circuit with a battery and a light bulb that will be on if there is current flowing from one end of the circuit to the other. But now we have two switches that are in parallel, like this. So notice that all we need for the circuit to be complete is one of these things, A or B, must be in the on position. So that gives us a different truth table, one that we've seen before. In the previous lecture, we wrote this as the disjunction of A with B. So this V, or this wedge symbol, is equal to Y. Some books and some websites will use the plus symbol to mean OR because the multiplication symbol really was AND. Now, I don't like this, and I want to show you why. If you look at the truth table, it is true for the first three rows that the OR function, so this Y, which this is A or B, is indeed 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, but then down here, 1 or 1 is 1. A lot of people, when they think of addition, Boolean addition, what they're really doing is they're doing what's called modular arithmetic, mod 2. So in other words, 1 plus 1, you might have seen this elsewhere. If not, we will do this in a later section. 1 plus 1 equals 0, mod 2. And you can think of this as just saying that odd plus odd is even. And that is different from what this is here. So this addition is not to be this OR symbol is not to be confused with addition modulo 2. And that's why I try not to use it. Sometimes what I've seen some people do is for addition modulo 2, they'll use a symbol like this. Now, if you are wondering how to represent an OR function with modular arithmetic, notice what this how to do this is this entry 1 right here is actually it's not quite a plus b, because a plus b mod 2 is 0, but if we take a plus b and then we add a times b, then this row works out. And that also doesn't change the value of the other 3 rows either, because for all 3 of these rows, a times b is 0. So actually, the correct way to do this modular arithmetic is that a or b is the same. Oh, I don't want to use that biconditional operator. Let's just say is a plus b plus a times b mod 2. And finally, schematically, we depict the OR logic gate like this. It's sort of like an AND logic. Remember the AND logic gate? If you don't, I'll just write it here. It was this like elongated D. So the OR logic gate is like that, but it's curved here. Looks more like a rocket ship. Of course, understanding digital circuits requires an understanding of Boolean logic. Recall that we have seen the following logical operations, and here they are by the truth tables. So P and Q, P or Q, if P then Q, if Q then P. We have the contrapositive of if P then Q, which is if not P then not Q, and then we have the biconditional operator P if and only if Q. I claim that if P then Q has the same truth table as this long expression. Let me try to break this down for you. So here we have 3 clauses. This first one is true if P equals 0 and Q equals 0. So that corresponds to this entry of 1. The next one is true if P equals 0 and Q equals 1. So that's the second row. And finally, this last one holds when P equals Q equals 1, and that's saying that this last entry is 1. So we can do this in any truth table. We could just look at all of the entries that are 1, and we can construct a bunch of clauses like this, and or disjunct them all together. Of course, another way we can write this, as we saw in the previous lecture, is just not P or Q. You can see that right here that this is the same as this is true when P is false or when Q is true. Similarly, Q implies P has the same truth table as this long expression. It's the one that we got up here, just reversing the roles of P and Q. I won't say it. Or just P or not Q. P if and only if Q has the same truth table as this expression. Let's do this for practice. Not P and not Q, which represents P and Q both being equal to 0, or P and Q, which represents the case when they're both equal to 1. Notice this first one happens when it says that when P and Q are both 0, the entry in the truth table is 1, and the next one says that when they're both 1, the entry in the truth table is 1. So unfortunately, this could not really be simplified beyond this the way that these can. And if you studied electrical engineering, perhaps you are familiar with the fact that the XOR gate is more complicated than just an OR gate or an AND gate. And this is an example of this. Not surprisingly, every Boolean function can be written with just and, or, and not. And hopefully, by looking at these examples, you see how to do it. Basically, just go down the entries in the truth table, and for every one entry, you can create an expression with not and as to how to set P and Q, or maybe there's more variables, to get out that one output, and then you can just AND all those expressions together, which is what we did here. However, even with just these three operations, many propositions are the same. For example, not P and Q and not P or not Q both have the same meaning. Let's introduce some terminology, and we'll do it with an example. So if we have P, Q, and R, which are propositions, then we can form a compound proposition. So here's an example. We can write C to be equal to P and Q, or not Q and R. And we say that this thing is generated by P, Q, and R. And of course, this is one example of many. There's infinitely many ways that we could string these things together. However, there are only finitely many possible functions that we can get that way. The value of C is determined by the 2 to the 3, or 8 possible combinations of truth values for P, Q, and R. If you don't quite see where that 8 comes from, let's look at the truth table. So here we have P, Q, and R, and there are 8 possible inputs. Those correspond to the rows. And if we have an unknown function C, not necessarily the one above, but there are 2 possibilities for each of these entries. And so in general, we have 2 to the 3, or 2 to the 8, or 256 possible functions C. Now that said, there are infinitely many, as I said earlier, infinitely many expressions that we can make by stringing these things together, because we can just keep going and going. So we'll have a lot of these compound propositions correspond to the same function. Okay, so let's now take this particular value of C right here, and let's build up the truth table for this. So we'll start by doing P and Q. That's this first clause, P and Q. Of course, the output is 0 for all entries except for the last 2, where P and Q are both 1. Next, let's do not Q. So not Q, 1, 1, 0, 0, 1, 1, 0, 0. Next, let's do not Q and R. So not Q and the value of R. So just to keep track, this will be 1 if and only if both of these are 1. So that's the second row and the 6th row. There are the 2 values of 1. And now let's OR these things together. So now we are going to take these 2 things, and the output is going to be 1 anytime that there's at least 1 1 in one of the rows. So that's going to be the second row and then the last 3 rows, and there are those 4 entries right there. Note that the first 3 columns are the numbers 0 to 7 in binary, and when I say are the numbers, I guess the rows in the first 3 columns. So this 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, 3, 4, 5, 6, and 7. And in general, if C is generated by n propositions, then its truth table will have 2 to the n rows. Here there's 3 propositions, and there are 2 to the 3, or 8 rows. Let's suppose that we have a set S of propositions. A proposition generated by S is any valid combination of propositions in S using conjunction, disjunction, and negation, and, or, and not. Here is a formal definition. If P is an element of S, then trivially, P is a proposition generated by S. Think of this as like the base case. Next, suppose that we have 2 propositions, X and Y, that are generated by S. Then, so are the following propositions. So X, sometimes parentheses around it, just emphasizes that we mean X itself. Also by symmetry, Y. Not X, X or Y, and X and Y. So from these, of course, we can put these together in many ways to get even a larger set of propositions. There is a standard order of operations. First comes negation, then conjunction, then disjunction, then the conditional operation, and finally the biconditional operation. Despite this, we will avoid writing potentially ambiguous statements like the following: P or Q and R. Now, technically this is not ambiguous, the parentheses do go here, but it's probably not automatic visually. So we like to include the parentheses when possible. You've probably seen those viral math memes, things like most people will get this wrong. 6 divided by 2 times 1 plus 2. What is this equal to? And of course, some people say, oh, this is 6 divided by 2 times 1 plus 2. Or others will say, oh no, this is 6 divided by 2 times 1 plus 2. And one of these is right based on the technical order of operations that we learned probably in grade school. And honestly, I don't know which one it is, because when I look at this, I say that's ambiguous. There's no reason you should ever write something like this because it's confusing. I have a PhD in mathematics. I don't know which one of these is right. Similarly, don't write things like this that are ambiguous. Always put parentheses in there if needed. That said, maybe there's a little ambiguity as to what is ambiguous. I will write things like not P and not Q. I think that is fine. Some books will insistently write parentheses around things, let's say not P and not Q, something like this. I think both of these are fine. I think that's certainly non-ambiguous. I certainly, before making this lecture, did not know that the conditional operator came before the biconditional operator. Like, let's just for fun, let's suppose we had P implies Q if and only if R. I guess technically this is saying that we do this one first. I don't think I would have guessed that. So take-home message is don't be ambiguous if at all possible. That said, expressions like the following should be unambiguous. P and Q and R is P and Q and R. Of course, we could put the parentheses here as well. This is an associative operation. I already showed this one to you. Not P or not R is not P in parentheses or not R in parentheses, so we usually omit the parentheses. And finally, a double negation, not P. We don't need parentheses. It's clear that that is not parentheses, not P, which of course is equivalent to just P. That brings us to the following definition. We say an expression involving logical variables that is true in all cases is a tautology. We use the number 1 to symbolize a tautology. Let's do some examples. Now, the following are all tautologies. So we'll start with one that says not P and Q, if and only if not P or not Q. So several comments. First of all, these outer parentheses on both sides are not required, but as I did say in the previous slide, I want to err on the side of being unambiguous. Next, let's check this with the truth table. So if we have P and Q, so 0, 0, 0, 1, 1, 0, 1, 1, then the left-hand side is not P and Q. So that's going to be the opposite of, so P and Q is true only when P and Q are both 1, otherwise it's 0, and a negation in front switches that. So that's going to make this 1, 1, 1, 0. And similarly, if we compute not P or not Q, this is always going to be true unless both the left and the right-hand side are 0, which happens when P is 1 and when Q is 1. So that's going to be down here is when it's false, and otherwise it's true. So both of these have the same truth table. So it is definitely true that the left-hand side is true if and only if the right-hand side is true. Our next example is P or not P. This has a very easy truth table. Only two entries, 0 and 1. Not P is the opposite, 1, 0, and we can check that P or not P. In both cases, 0 or 1 is 1. In the next case, 1 or 0 is 1. So this is a tautology because all of the entries in the truth table are 1. Next, P and Q implies P. Let's check this one. So we have P, we have Q. Let's do the truth table, P and Q. So let's just start with this, 0, 0, 0, 1, 1, 0, 1, 1. P and Q is 0, 0, 0, 1. And then, now before we continue, this does make sense. If P and Q are true, then P is true. But as we've seen, sometimes our intuition can mislead us when we're dealing with truth tables, especially when we have something like P implies Q, that returns 1, that returns true if P is false, which may or may not have been intuitive the first time you heard it. So just to be safe, let's make sure that this does match the definition of a tautology. Okay, so P and Q implies P. So let me actually just put an extra P here. So P 0, 0, 1, 1 here. And so remember, 0 implies 0 is true. 0 implies 0 is true. 0 implies 1 is true. And 1 implies 1 is true as well. The only one that's not true, remember, is that 1 does not imply 0. Okay, so that is a tautology because all of these entries, this really is the column that belongs here, all of these entries are 1, so it is a tautology. Next is, in some sense, the dual of this third one. It says if Q is true, then P or Q are true. That certainly makes sense intuitively, but let's check the truth table again. So let's check P and Q. Let's try all the inputs. 0, 0, 0, 1, 1, 0, 1, 1. Let's do P or Q. So this is 0, 1, 1, 1. And now let's try Q implies P or Q. So that's just what you get when you take these two columns here. This implies that. So 0 implies 0 is true. 1 implies 1 is true. 0 implies 1 is true. And 1 implies 1 is true. Once again, remember the only time you get 0 in an implication is when you have 1 implies 0 and you don't have that here. Finally, P or Q, if and only if Q or P. That is the tautology. I will skip the verification and leave that as an exercise. Finally, we conclude with a definition of the opposite of a tautology. An expression involving logical variables that is false in all cases is a contradiction. We use the number 0 to symbolize a contradiction. I'll show you two contradictions. The first one is P and not P. Let me draw the truth table for that. So P, 0, 1, not P, 1, 0, and P and not P is just the conjunction of these two. So in both cases you get a 0 with a 1, and the conjunction of that is 0. So for all choices of input, you get 0, And notice that if I had defined a new function and I call it 0, then just by definition, this is the constant function that always returns 0. And what we're saying is that this function is in some sense equivalent to the function 0, the constant. And we'll formalize that in the next lecture. Okay, next. P or Q and not P and not Q. So let's just check that. So we have P and we have Q. So 0, 0, 0, 1, 1, 0, 1, 1. These are all the inputs. P or Q is 0, 1, 1, 1. Not P is 1, 1, 0, 0. Not Q is 1, 0, 1, 1. And then if we are going to AND these expressions, let me call this one, using our notation from earlier, C. So let's call this one C. This is just the AND of these three entries. And in all of these cases, we get 0 because at least one of them is going to be false. So we will write that C is, this is a notation that I will introduce in the next lecture, is equivalent to 0. Okay, so in the next lecture, we will formalize what we mean by equivalence like this, and also something weaker, which is called implication, when something like C maybe implies D, but is not equivalent to. So that's coming up soon. Stay with us.